Hello and welcome to the AC version of Kirchhoff's laws. Apart from knowing Kirchhoff's laws, about the only other thing you need to know at level 0 is the fact that a 180 degree phase shift is equivalent to multiplying an AC waveform by -1. That's because if I take an AC waveform something like this, then 180 degrees would be 1/2 of a period. Remember, that is a whole period, therefore 360 degrees. Half that period would be 180 degrees, and that's the time between a peak here and a minimum here. If I move the entire waveform by that much, by 180 degrees, then that positive moves 180 degrees and goes there. That 0 moves 180 degrees, ends up there. That negative moves 180 degrees and goes there. That 0 there moves 180 degrees and goes there, and so on. And the waveform that I get as a result is this, which is exactly the original waveform upside down. So 180 degrees phase shift is equivalent to multiplying by -1. That's about all you need to know. Let's try some problems. This one is even easier than that because both of the phases of the voltage sources here are 180 degrees. So we can just use Kirchhoff's law as we have done before, because we know that all of the voltages in this circuit are going to have a phase of 180 degrees. So we have 17 volts here, 8 volts here. What's missing, and what would be read across this voltmeter, must be 17 minus 8, which is 9. So that's just 9 volts at 180 degrees. Let's see if we can find... here's another one. 18 volts from here to here at 0 degrees, and that's 8 volts from here to here, but at 180 degrees. Now if that was 0 degrees, then the voltmeter would be reading 10 volts. Because I'd need the 10 volts there plus the 8 volts there to give me 18 volts there. But it's not 0 degrees, it's 180 degrees, which effectively means this 8 volts is actually minus 8 volts at 0 degrees. So what I've got here is 18 volts here and minus 8 volts at 0 degrees here, which means the voltmeter there is going to have to be reading 26 volts at 0 degrees. Fine. You can do these things just by using the complex numbers. For example, we've got 12 volts here and 5 volts at 0 degrees there, so the voltage across here must be 12 volts at 180 minus 5 volts at 0, exactly as if we were doing it in DC, except using the complex numbers instead of just the magnitude of the voltage. And we could write the answer as 12 volts at 180 degrees minus 5 volts at 0, and that would do. It would work out that the result is 17 volts at 180 degrees. Let's see if we can find a current one. Here we go, a current one. 6 milliamps at 0 degrees and 2 milliamps at 0 degrees. The current flowing into this node must equal the current flowing out of that node, so that just must be 6 milliamps at 0 degrees plus 2 milliamps at 0 degrees. Oops. 8 milliamps at 0 degrees, fine. And at 180 degrees like this, again, both of the phases are 180 degrees, so we know the current here must have a phase of 180 degrees. All the phases are the same. We could just write that as 11 milliamps at 180 degrees, and we're done. But if the phases are different, like this one, well, we could do that as the unknown current here must be the current going out of the node minus the other current going into the node. So that must be 8 milliamps at 0 degrees minus 7 milliamps at 180 degrees, and it would calculate the answer, 15 milliamps at 0 degrees here. Or we could just note that 7 milliamps at 180 degrees is minus 7 milliamps at 0 degrees, using the fact that a phase shift of 180 degrees is equivalent to multiplying by minus 1. So that's actually 7 milliamps at 0 degrees going this way, right to left. And in that case, I could say, well, the unknown current here must be the 7 milliamps at 0 degrees going this way, plus the 8 milliamps at 0 degrees going that way. The answer, therefore, must be 15 milliamps at 0 degrees. It takes a little bit of getting used to, but hopefully not too bad.